In this presentation, I'll go through some notes from Chapter 9 of Designing Data-Intensive Applications. Chapter 9 is called Consistency and Consensus. So here's a beautiful diagram from Chapter 9. As you can see, in the picture there is global constraints, linearizability, distributed transaction, total order broadcast, timestamp ordering, all very interesting topics. So let's dive in. So this chapter examined the topics of consistency and consensus from several different angles. We looked at in-depth at linearizability, a popular consistency model. Its goal is to make replicated data appear as though there were only a single copy and to make all operations act on it atomically. Although linearizability is appealing because it is easy to understand, it makes a database behave like a variable in a single-threaded program. It has the downside of being slow, especially in environments with large network delays. It also explored causality, which imposes an ordering on events in a system. For example, what happened before or based on cause and effect. Unlike linearizability, which puts all operation in a single totally ordered timeline, causality provides us with a weaker consistency model. Some things can be concurrent, so the version history is like a timeline with branching and merging. Causal consistency does not have the coordination overhead of linearizability and is much less sensitive to network problems. We saw that achieving consensus means deciding something in such a way that all nodes agree on what was decided, such that the decision is irrevocable. With some digging, it turns out that a wide range of problems are actually reducible to consensus and are equivalent to each other, in the sense that you have a solution for one of them, you can easily transform it into a solution for one of the others. Such equivalent problems include linearizable compare and set registers, that is, the registers needs to be atomically decide whether to set its value based on whether its current value equals the parameter given in the operation. Atomic transaction commit database must decide whether to commit or abort a distributed transaction. Total order broadcast. The messaging system must decide on the order in which to deliver messages, locks and leases. When several clients are racing to grab a lock or lease, the lock decides which one successfully acquired it. Membership coordination service. Given a failure detector, example timeouts, the system must decide which nodes are alive and which should be considered dead because they are certain timeline. Uniqueness constraint. When several transactions concurrently try to create conflicting records within the same key, the constraints must decide which one to allow and which should fail with a constraint violation. If that single leader fails, or if a network interruption makes the leader unreachable, such a system becomes unable to make any progress. There are three ways of handling that situation. First, wait for the leader to recover and accept that the system will be blocked in the meantime. Second, manually fail over by getting humans to choose a new leader and reconfigure the system to use it, or use an algorithm to automatically choose a new leader. Although a single leader database can provide linearizability without executing a consensus algorithm on every write, it still requires consensus to maintain its leadership and leadership changes. Tools like Zookeeper play an important role in providing an outsourced consensus, failure detection, and membership services that applications can use. So here are some of the highlights from the chapter. Linearizability. In an eventual consistent database, if you ask two different replicas the same question at the same time, you may get two different answers. That confuses you. Would it be a lot simpler if the database could give the illusion that there is only one replica? Then every client would have the same view of the data and you wouldn't have to worry about replication lag. This is the idea behind linearizability, also called atomic consistency, strong consistency, immediate consistency, and external consistency. The exact definition of linearizability is quite subtle and we'll explore it in the rest of the section, but the basic idea is to make a system appear as if there were only one copy of the data and all operations on it are atomic. In the linearizable system, as soon as one client successfully completes a write, all clients reading from the database must be able to see the value just written. Linearizability is easily confused with serializability, as both words seems to mean something like can be arranged in sequential order. However, there are quite different guarantees and it is important to distinguish between them. Serializability. Serializability is an isolation property of transactions where each transaction may read and write to multiple objects. For example, rows, documents, records. It guarantees that the transaction behave the same as if they had executed in some serial order. It is okay that the serial order to be different from the order in which the transaction were actually run. Linearizability is a recency guarantee on reads and writes of a register that is an individual object. It doesn't group operations together into transactions, so it does not prevent problems such as write skew unless you take additional measures as neutralizing conflicts. A database may provide both serializability and linearizability, and this combination is known as strict serializability or strong one-copy serializability. Implementation of serializability based on two-phase locking or actual serial execution are typically linearizable. However, serializable snapshot isolation is not linearizable by design. It makes reads from a consistent snapshot to avoid lock contention between readers and writers. The whole point of consistent snapshot is that does not include writes which are more decent than that snapshot, and thus the reads from the snapshot are not linearizable. Highlights. Total order broadcast. Total order broadcast is usually described as a protocol for exchanging messages between nodes. Informally, it requires the two safety properties always be satisfied. Reliable delivery. No messages are lost. No messages are lost. If a message is delivered to one node, it is delivered to all the nodes. Total order delivery. Messages are delivered to every node in the same order. A correct algorithm for total order broadcast must ensure that reliability and ordered properties are always satisfied, even if a node or a network is faulty. Of course, messages will not be delivered when the network is interrupted, but an algorithm can keep retrying so that the messages get through when the network is eventually repaired. Hope this was useful. Have a nice time. Like and subscribe for more such content.